Welcome to this session on statistical quality control. Today, we are going to explore two incredibly powerful techniques used by statisticians and engineers worldwide: base shifting and splicing. Imagine trying to compare the cost of living today with the cost of living 50 years ago. Direct comparisons often fail because the baseline is just too old. How do we fix this? How do we connect historical data with modern metrics without losing the underlying trends? That is exactly what we will learn today. Let us dive in and make sense of these essential tools. Let us start with our first major concept: base shifting. Why does this matter? Imagine you're tracking your weight over 10 years. If you always compare your current weight to what you weighed in high school, the comparison eventually loses its meaning because your body has naturally changed. You need a more recent baseline. In statistics, an index number measures how much a variable changes relative to a base value, which is always set to 100. Over time, that starting point gets too old and irrelevant. Base shifting is the statistical technique we use to mathematically move that reference period to a more recent, relevant year. We are simply resetting the 0 point on our measuring tape to a more convenient spot without having to gather all the raw historical data again. Now that we understand what base shifting is, let us look at how it works mathematically. The formula comes from a simple proportional relationship. We want to scale our current data so that our chosen new base year becomes exactly 100. In this equation, IN represents the newly calculated index number for a specific year after the shift. IC stands for the current year's original index number from the old series. IB represents the old index number of the specific year we have chosen to be our new starting baseline. Finally, we multiply by 100 because index numbers are traditionally expressed as percentages relative to the base. If the value of IC increases, the new index IN also increases, maintaining the exact same proportional relationship as the original data. Before we move on, let us see this with a concrete example. Suppose we have an index series with the year 2010 as the base. We are given that the index for the year 2015 is 150 and the index for the year 2018 is 180. We want to shift the base year to 2015, meaning we need to find the new index for the year 2018. Why do we choose this formula? Because we need to recalculate the 2018 index so that the year 2015 acts as the new baseline of 100. We identify our variables. 180 is our current year's old index, and 150 is the old index of our new base year. We set up our standard base shifting formula to scale the old data to the new reference point. Continuing with our calculation, we substitute 180 for the 2018 index and 150 for the 2015 index. Dividing 180 by 150 gives us a ratio of 1.2. This intermediate step tells us that the measured variable in 2018 was 20% higher than it was in 2015. Finally, we multiply by 100 to normalize it to our index scale. The new index for 2018 with 2015 as the base is 120. This physically means that between 2015 and 2018, there was a 20% increase in the measured variable, preserving the original trend perfectly. So, we have successfully shifted a base year. This brings us to another common challenge: splicing. Imagine you are building a long bridge, but you started building it from two different sides of a river using two different measurement systems. When the two sides meet in the middle, you need a way to connect them smoothly so traffic can drive across without hitting a massive bump. In statistics, splicing is how we connect two different index number series that overlap at a specific point in time. Often, a government or company will stop an old index series and start a brand new one with a new base year. If a researcher wants to look at a long-term trend, they cannot just put the numbers side by side because the baselines are completely different. Splicing mathematically welds these two series together at their overlapping year, acting exactly like a currency exchange rate. Now that we understand the idea, let us look at a visual representation of splicing. On this graph, the horizontal axis represents the years and the vertical axis represents the index value. Notice the solid blue line. This is our old series, starting at a base of 100 in 2010 and growing over time. Then, look at the solid red line. This is our new series, which resets to a base of 100 in the year 2020. The circle where they meet in 2020 is our overlap point, or splicing year. The dashed green lines show the magic of splicing. The upper dashed line shows forward splicing, extending the old series into the future. The lower dashed line shows backward splicing, extending the new series into the past. This diagram beautifully illustrates how splicing creates a single continuous historical record. Having seen the visual, let us focus specifically on the upper dashed line, forward splicing. Why do we use this specific technique? We use forward splicing when we want to keep the old base year and extend the old series forward into the future using newly collected data. We are essentially translating the new series backward into the mathematical language of the old series. This is highly useful when a company has decades of historical data and wants to see how current performance stacks up against that original long-standing baseline. By forward splicing, the new data points are scaled up to match the larger numbers that the old series reached before it was discontinued. It allows us to maintain a consistent historical perspective without losing the context of our original starting point. This concept leads us directly to the mathematical formula for forward splicing. Conceptually, we are taking the new data point and multiplying it by a conversion factor established at the overlap year. Here, the symbol IF is the newly calculated forward spliced index that continues the old series into the present. The term IX represents the value from the new series that we want to convert. The term IY is the value of the old series at the exact year where both series intersect and overlap. We divide by 100 because the new series has a base of 100 at the overlap year, acting as our conversion factor. As the new series grows, this formula scales that growth proportionally to match the larger numbers of the older series. If the new series value increases, the forward spliced index increases accordingly. Let us apply this formula to a practical scenario. An old index series ends in the year 2020 with a final value of 150. A new index series is immediately started with 2020 as its base year, meaning its value in 2020 is 100. In the year 2021, the new series reaches a value of 110. We are asked to find the index for 2021 as if the old series had simply continued without interruption. We choose the forward splicing formula because we are projecting the old baseline into the future. The overlapping year is 2020, where the old series value is 150. The new series value we want to convert into the old scale is 110. Continuing our calculation, we substitute 110 for the 2021 new series index and 150 for the 2020 old series overlap index. Multiplying the numerator values, 110 times 150, gives us a total scaled value of 16,500. We then normalize this by dividing by the base of 100. The forward spliced index for 2021 is 165. What does this mean physically? This means that if we had never changed the base year, the index in 2021 would be 165. This allows for a direct apples-to-apples comparison with data from years prior to 2020, showing continuous growth. Now that we have extended data into the future, let us look at the reverse process, backward splicing. Backward splicing is the exact opposite mathematical process of forward splicing. Instead of dragging the new data into the past, we drag the old historical data into the present. Why is this necessary? We use backward splicing when we want to adopt the new base year as our standard, but we still want to see what the historical data would look like under this new modern baseline. This is crucial when a new standard is established, and all past performance must be re-evaluated against this new benchmark to see how much things have truly improved. It gives us a modern lens through which to view historical achievements. To achieve this modern perspective, we use the backward splicing formula. Conceptually, we are taking an old historical value and shrinking or scaling it to fit the new, lower baseline established at the overlap year. In this equation, the symbol IW is the historical data point translated into the new series' modern scale. The symbol IZ is the original historical value from the old series that we want to convert. The symbol IY is the value of the old series at the specific year where the transition and overlap happened. We multiply by 100 to scale the historical data to the new base. If the historical value was lower than the overlap value, the resulting backward spliced index will correctly be calculated as less than 100, reflecting that past values were smaller than the new standard. Let us see how this works with our final example. Using the same overlapping data as before, the old series ends in 2020 with a value of 150. The new series starts in 2020 at a base of 100. We are given that the old series has a value of 120 in the historical year 2015. We want to translate this 2015 historical index into the scale of the new series. We choose the backward splicing formula because we need to pull historical data forward to the new modern baseline. The overlapping year is 2020, where the old index is 150. The historical value we want to convert is 120 from the year 2015. Let us finish the calculation. We substitute 120 for the historical 2015 index and 150 for the overlap year's old index. We multiply the numerator 120 times 100 to get an unscaled total of 12,000. We then divide this by the overlap reference value of 150. The backward spliced index for 2015 is 80. What is the physical meaning of this result? This physically means that in 2015, the measured variable was at exactly 80% of its 2020 level. By doing this, we have gained a clear historical perspective using the modern baseline, allowing us to see exactly how much growth occurred leading up to the new standard. We have covered a lot of ground today, so let us summarize the key takeaways. First, base shifting is an essential tool that updates our reference point to a modern standard, preventing us from making comparisons against ancient history. Second, splicing acts as the mathematical glue that holds different eras of data together smoothly. We learned that forward splicing allows us to extend old baselines into the future, preserving long-term historical trends. Conversely, backward splicing lets us evaluate historical data against new modern benchmarks. Without these techniques, engineers and analysts would be completely unable to track long-term trends accurately whenever a measurement baseline is updated. You now have the mathematical tools to maintain the relevance and continuity of long-term data. Great job today!